So, good morning. Welcome to Krishna's classroom. Today it is Teachers' Day, and let me wish every teacher a very happy Teachers' Day. And I hope their dedicated services to the society will kindle new flames for the posterity. On this occasion, I wish to dedicate this lecture to late Dr. Mrs. Jyoti Das, who was professor at IIT Madras, IIT Kharagpur, and at the University of Calcutta during her teaching career. An excellent teacher and a wonderful human being, and I was distinctly fortunate to have worked with her for my PhD. I dedicate this lecture on this day to late Dr. Mrs. Jyoti Das, my beloved teacher. Thank you very much. Now let me continue from where we left last time. The third part of this lecture, we introduce the concept of orthogonality in inner product spaces. And we also introduced the orthogonal complement of a given set. And we found that if S is a subset of the inner product space, then S perp is a subspace of the vector space. This is what we have seen, and we have also seen that for any S, S is contained in S perp perp. Recall the notation that we have introduced last time. Okay, now we continue with this. But before that, let me just introduce some usual terminologies that we use, and we shall define an inner product. So, we define an inner product V is the inner product space as a Hermitian symmetry this corresponds to the part that sesquilinear corresponding to linear in the first variable and conjugate linear in the second variable. And positive and a the third one corresponds to so these are the three distinct attributes of the inner product. First of all, it is Hermitian symmetric. This is sesquilinear. It is also called, okay, sesquilinear is also called conjugate bilinear. Now the conditions on also implies norm x, which is equal to the power half, satisfies the homogeneous mode. The homogeneity property. Namely, norm of alpha x equal to mod alpha norm of x. Now, if the associated field is R, then of course you call this simply symmetric. This is symmetric, this is bilinear, and it is positive definite form. So this is the word you have, positive definite form. These are the three attributes that you have for the inner product. Now this is also the other terminology that is used. Sesquilinear is sometimes called conjugate bilinear. Now the conditions also imply that this is norm of x, satisfies the homogeneity property. Okay. Now we introduce the definition of an orthonormal set. Vectors in the inner product space V is said to be orthonormal if the following conditions are true. That is namely for every uv belonging to U, uv inner product of this is equal to 0 whenever u is not equal to v, and the inner product of u with v is equal to 1 this is the condition. Then you say this is an orthonormal set. Now it is quite possible that this set may be finite or infinite depending on the space. For example, you take R3 with the usual inner product. You take U to be the following collection. This is a subset of V, and you see that it can be a finite set. In fact, for on Rn, if you take Cn, where delta ij is of course the usual Kronecker delta. That means delta Jij equal to 1 whenever I equal to j, otherwise it is 0. So this is the standard basis that you choose for Cn. Then this is orthonormal. And this is for the unitary space. That means the usual inner product is defined as the dot product. The third example is that it could be infinite. There are several examples that you can give in this regard. Like you take V to be equal to minus pi to pi with the inner product f Then you look at the functions. Look at the functions. So you look at this collection of functions. 1, sin nx. This collection of vectors. Now you see that this is an orthonormal. This is that is you see the whenever n is not equal to m, the same is true for whenever n is not equal to m, and you have or I think I will rework with yeah, it's okay. This is equal to 0 for all n and m, whether they are equal or not, and you have what is that? Etc. So this is about the orthogonality. Now what you do is you can normalize this. Okay. So you normalize each of this. What you do is 1. So the inner product of 1 with 1 equal to what you get as 2 pi, and you take inner product of or cos nt and call each one of this is norm of 1, norm of define this. And now with this you see that so 1 by root pi, then 1 by square root of 2 pi, and then 1 upon this collection with n equal to this collection of infinite sets form an orthonormal. It's an example of an infinite orthonormal set. So what I wanted to tell you is that, I mean, this you know where it occurs in the Fourier series. Okay. So there are other sort of things, Legendre polynomials are there, Logger polynomials are there. There are several such orthonormal functions that one can define. Maybe we will visit some of them, or at least make a mention of some of them when we go further, and especially when we come to what is called the orthogonalization process, what is called the Gram-Schmidt process. In that context, I think we will revisit these things. But what I wanted to say was, it is not necessarily a finite set, but it could also be an infinite set. Okay, so these are the examples for that. Now we make certain observations on this. We first observe that every orthonormal set in an inner product space is a linearly independent set. That's the result that we want to prove. Okay, so we make a special mention is this. It's not necessarily the standard basis that become orthonormal, but in every vector there are several orthonormal sets that you can possibly have in a inner product space. Okay, so let me make a remark. If UN say. Then U is orthonormal. Right. Okay, now we look at the properties of this orthonormal sets. It's very useful class because it eventually would give you a sort of basis for your space which has the nice property of orthonormality. And the fact that this particular set has the orthonormal property means all your computations are going to be simple. I will explain this later when it comes to that. So we make this remark and then let us first make an observation. An orthonormal set is linearly independent. Now, if you are talking about the linear independence of a finite set, then it means that suppose U1, U2, etc. Un is a finite set which is linearly independent, then it means that sigma alpha I ui equal to 0, 0. This we have seen. This is the definition of the linear independence for I equal to. This is for a finite set. Now, what does it mean to say that an infinite set is linearly independent? This should be very clear because you see that this sum has a meaning in the context of the linear space structure only if it's a finite sum. Otherwise, it doesn't have any meaning unless you have some more structure on it, and which we shall see, we shall make use of later. But right now, we have only this linear space structure and just an inner product. We have not gone beyond that. And we say that an infinite subset of an inner product space, or for that matter of a linear space, is linearly independent if and only if every finite subset of that is linearly, that collection is linearly independent. Okay, because we already know the linear independence we have defined for finite collection. Okay, so recall that where of course this is the meaning of linearly independence for a finite set. Now in bracket, if you want, you can write a finite set So that is the definition of linear independence for a finite set, where of course alpha i's are real or complex numbers, since we are working in the context of inner product spaces. This is a very general definition. Therefore, suppose U is a let now what we do is we show that this is linearly independent. That means an arbitrarily chosen for every finite subset of the orthonormal collection is linearly independent. Okay. Okay. So how to prove this? Consider a linear combination given by alpha j say call this U. We claim So that u equal to 0 implies 0 is equal to the inner product u with uj, which is equal to alpha j ui. ui, this is equal to sigma alpha j okay, and of course I belonging to which implies this is here we have used that is the orthonormality. Zero equal to alpha, and this is true for every I. What does it mean? It means so this is where we have used the orthonormality of the set. Now, since the choice of u is arbitrary, shows that for every finite set this happens. Thus, every finite set Okay. So this is one property that the orthonormal sets do possess, which is extremely advantageous. Now you see, clearly linearly independent sets in an inner product space need not be orthonormal, but all orthonormal subsets of an inner product space are linearly independent. Okay, so remark orthonormal. But all orthonormal So that opens up a lot of questions, because we have certain advantages in the computation when we use orthonormal sets. So the question comes that given an inner product space, does there exist an orthonormal set at all? I mean, that can be easily answered. Okay. Right? But if you go beyond that, when you need more machinery to resolve the issue. Okay. So the questions that you ask are, yes, if the inner product space is non-trivial, yes, it happens. Okay. So the answer to this is yes. V is not equal to just the vector space consisting of the zero element. Right. To prove this, so since equal to 0. Now Now V means it is defined through the inner product. This is the but there are questions like can you get of course there are a lot of examples where you can get it, but in general, can you show that in a vector space there is a subset consisting of more than one element which is orthonormal? We are not at the moment in a position to answer this, but certainly we'll give an answer to this. Okay, we'll postpone the answering that question for later. So the question that you have to ask is this. At this stage, okay. But we shall prove it later. This question, so you know, when we do the orthonormalization process, okay, so we take up this question. Now we define a new terminology. Complete orthonormal set. We now define what is called a complete orthonormal set. Is said to be complete if it is a maximal orthonormal set. That is, it is not a proper subset of So it is maximal in the sense that you cannot conceive this as a part of a larger orthonormal set. Give some examples, then it will be clear. You take this 2. Where EI this is the standard, this is the standard orthonormal basis that we normally use. Now you see that you cannot put in an extra element into this collection and still have that new collection orthonormal. Why? Because suppose you put, I'll just give a quick proof of this. Suppose you make it this. And put an x1 consider this collection and demand that this is an orthonormal set. If you demand that this is an orthonormal set, then you see that, this is orthogonal to the first one, give you have x and I can say x ei equal to 0 implies xi equal to 0 for I equal to 1. What does it mean? This set is orthonormal. Then the only possibility is that x1, x2, x3 is 0, the 0 vector, and that is not, so you don't have any orthonormal enhancement of this set, okay, or this cannot be a part of any larger orthonormal set, or in a sense this is a maximal orthonormal set. On the other hand, suppose you take the first example, second example, you take the following. With the usual linear product, I want to make this orthonormal, therefore I will have it 1 by So you can check that this is orthonormal. This is orthonormal. Now what we want is this. Let us see. Suppose you are joined to this. Where we take x1 square plus x2 square plus x3 square equal to 1, that means the dot product of this. So you see you get two equations here by orthonormality. What is that? This is equal to 1 by zero, that is x1 plus and this third equation, the second equation is, so if you take any x1, x2, x3 such that x1 plus x2 equal to 0 and then, and of course x1, x2, x3 such that x1 square plus and there are plenty of choice of this. You can choose x1 and x2. So all that you need is choose this. Choose x minus x 0 with the property that 2x square equal to 1. There's plenty of choice for this. Okay. If you adjoin that to this set, then it becomes a orthonormal set. So so this is not something which is maximal, and therefore this is not, therefore complete. Now other examples are, see, you take because we are not going to give any proof for that, the collection of functions that we have looked at, 1 cos nx, sin nx for n ranging from 1 to infinity with appropriate normalization. Normalization means divide by the norm of each of these functions. Then that collection is an orthonormal set. Is it complete? That needs some work to prove it. In fact, it is. Okay? That we can prove later. But certainly if you just consider 1 by norm 1 cos this collection, this subcollection for n equal to, it's an infinite collection though. It's a proper subcollection of the collection that we have looked at. Certainly this is not complete because you can bring in all those sin nx divided by norm of sin nx into this, and it's a larger set which is orthonormal. Okay, so we will we just I think these examples are sufficient to give you a feel for the problem. Okay, so what is the advantage of having complete orthonormal spaces? Now you see, as I said, in an inner product space there may be several orthonormal sets. Now you see that every complete orthonormal set is linearly independent. That's obvious. So we'll okay. Now we just confine ourselves to the finite dimensional vector spaces. So finite dimensional vector space. Then talk about what is called the orthogonal dimension. So then one statement that you can make is that let equal to n. What we can say is that every orthonormal or subset of V cardinality less than or equal to. Okay. Well, the proof is very simple. Suppose you take suppose you have the a subset which has got more than n, which is orthonormal and has more than n elements. Then what can you say? orthonormal subset of V and cardinality of then U is a linearly dependent set. Having m elements. Therefore, m is less than or equal to dimension of V, which is equal to n. So at most you can have n elements in a complete orthonormal set, especially so every complete orthonormal set at most that is an inference that you can immediately make. Once you assume the dimension of the space is equal to n. The question that you want to address is this. Again, we will have to wait for some more time to answer this question. Okay? Right? So we shall leave a definition which we shall not need later. We shall define the following. The orthogonal dimension of an inner product space is the largest and see, this is again poses lot of problems. Okay, this is okay. So you have one orthonormal. How do you know that two different complete orthonormal sets in an inner product space has the same number of elements? I mean, you had this problem initially. I mean, you know, when we were working on the cardinality of the basis, or what you call the dimension of a vector space. In the case of the finite dimensional vector spaces, we had this problem. Namely, you take two linearly independent, because we know that there are there's a variety of choice of linearly independent spanning sets in a vector space. Do they always have the same element, same number of elements? Yes, this question we have solved in the beginning. I mean, you recall the proof of such things. Now, a similar problem arises here. Suppose you take two different complete orthonormal sets in an inner product space. Do they have the same number of elements? So, question. Two B. Do they have the cardinality? That is why I think we have said the largest number of vectors in an orthonormal set that you may have in the space. So this is not, it's not at the moment we can answer this, but we will certainly find an answer to this question. In fact, we show that in a finite inner product space, you have, if you take any two complete orthonormal sets, they have the same elements, same number of elements, and it is equal to the dimension of the space. This is something that we are going to prove. So all this you will have to wait until we introduce the so-called Gram-Schmidt process of construction of orthonormal vectors from a basis for a inner product space. Okay. Now we shall prove the so-called Vessels inequality. Let us take R3. Okay. right? So before we make the statement of this, consider ortho. Now suppose you take a what do you call this x and y? These two vectors. So they are linearly independent vectors, and assume that this is an orthonormal set. Now you choose any vector z. Okay. So let now you take the projection of z in R2. What will happen? So you are taking a vector whose length is equal to 1, and now you take a vector y and project it onto this. What will happen? Take the orthogonal projection. This you can actually see is the following, that is the projection of, okay, so okay, the projection of the orthogonal projection and we have of course norm of x is what? See, you complete the parallelogram. You want to find out this. Now you want to find out this. So you are taking the orthogonal projection. So you take so remove from y, this is y, okay. This is given by this particular vector. This is the orthogonal projection. Okay, so my claim is this. Okay, so my claim is this. So you take, say, first let us consider the simple case R2. Take the vector E, so not E, X, such that norm of x equal to 1. This is an orthonormal set. Now let y belong to R. Now you take the projection of y to orthogonal projection of that is along the vector x. What is that? We claim that this is the orthogonal projection. Okay. Y it's quite easy to see that this is the orthogonal projection. You can show that y minus is orthogonal to x. That is, this is the vector y minus x. This is the vector. You can show that this is orthogonal to this. How do you show that it's orthogonal to this? Just take the dot product with x. What you get? You get yx minus yx, which is equal to 0. That means you prove this. Now you do the same thing, what you do for R3. Now we work with R3. So consider R3. Is an orthonormal what is the orthogonal projection Z span of now you see that this is a linear combination of x and y. Let it be denoted by Z prime, which is equal to beta y. Now we want alpha x plus beta y orthogonal to, and we want this has the orthogonal projection of this. What does it mean? It means you want z minus z prime to be orthogonal to xy or the span of xy. This means z minus z prime is orthogonal to x and y. And this is an orthonormal set. So norm of x equal to 1, norm of y equal to 1. So we have norm of x equal to 1, norm of y equal to 1, inner product of x with y equal to 0. This is what you have. Now, what is z prime? Z prime is taken as this. Therefore, you need z minus alpha x plus orthogonal to x so let us do that. So what is it? You have z inner product with x minus alpha into but this is 0, that is alpha is equal to, similarly beta equal to z prime. Okay, therefore z prime, the orthogonal projection z prime is equal to this is the orthogonal projection to the space spanned by x and y. Okay. So you are taking a z and then projecting it to as a vector here. This has to be, so this is going to get projected to this vector, and that's a linear combination of x and y. So what you have is this, there is a plane spanned by x and y. So x is here, this is x, this is y, and then you take any z, project it into this space. This is the orthogonal projection. So this is z and this is what you call z prime. Z prime is written as, see, your usual resolution of a vector into this. Okay, so this is what you get, right? Now, what are the consequences of this? Immediately see that the length of z prime This is an inequality that you get. Okay. So we are trying to find out whether this is going to be true in general, and this gives what is called the Vessels inequality. Okay. So let me just state the Vessels inequality, then give a proof of that. The useful result with a lot of ramifications gives some insight into the space. Okay. So we Vessels inequality. Any finite orthonormal set V V belonging to V, let that is the following sigma this is true for every V. Now further V prime orthogonal to Uj, each Uj span of U. Okay, let us prove this. I mean, the proof is very simple. It's already contained here. So you see that this one, you just compute this. 0 is less than or equal to V prime inner product of V minus alpha I ui where of course alpha I is as given to you. Now this you can compute, you compute this is equal to minus sigma alpha I ui V minus sigma what is it, alpha I conjugate V ui plus okay j alpha I alpha j conjugate ui uj. Okay, this is the summation that you get if you expand it, and you see that this will give you, so this is alpha I conjugate. Now this is alpha I conjugate alpha I, and this is actually sigma alpha I conjugate. So this is equal to, I mean that's very simple to see. Quickly write it up and expand it and then write it up. So we have this is equal to alpha I square, and that gives you the following This is true for any. That is, you have in fact in terms of the inner product, this is I equal to 1 to n mod so this is the famous Vessels inequality. This is true for any orthonormal set. Now later on we shall see what happens if your orthonormal set is a complete orthonormal set. That we shall consider next time, and it is quite a direct computation to show that or one can easily verify that V prime that means V prime is orthogonal to n, that is V prime is orthogonal to, belongs to span of that completes the proof. Now this is a simple computation, direct computation. You have the expression for V prime, take dot product with Ui, use orthogonality. That's all. It's a very direct computation. Okay, so thank you very much. Once again, I wish every teacher on this earth a very happy Teachers' Day, or at least in India, because in India it is considered as a Teachers' Day, and it is the birthday of our former president, late S. Radhakrishna, who was a great scholar and a great teacher. Thank you very much.